All right, cool. So this video is going to be all about the kinetic molecular theory, also known as KMT. So what is the kinetic molecular theory? So there's four postulates that are just going to describe um, gas behavior under ideal circumstances. So this is an important distinction between ideal and real gases. So these ideal gases, so what have we talked about in the past videos? We talked about Charles' law, Avogadro's law, the ideal gas law, the combined gas law, Boyle's law. So all these have ideal conditions associated with them, right? Right. So essentially, it's perfect conditions, and it makes both the math easier and the conceptual understanding easier. But in the real environment and on Earth, gases don't always follow these rigid and perfect conditions, right? There's going to be more flux, there's going to be more change and variation in how the gases behave. And we'll talk about it in later videos. Sometimes pressure and volume is going to play a heavy role in how ideal a gas will behave, right? Okay, so going back to the KMT, the kinetic molecular theory, there's going to be four postulates, right? And these are basically all the perfect conditions that for an ideal gas. So first one is that there's no attraction or repulsion between gas particles. This is going to decrease energy flux, so there's energy conservation, right? Two, there's gas particle size is considered to be negligible, and particles are adequately spaced and separated from each other. Three, gas molecules are in constant and random motion. And four, the average kinetic energy of an ideal system, ideal gaseous system, and is dependent upon Kelvin temperature. So there's that constancy there, and it's dependent upon the Kelvin temperature. Ke equals 3/2 times R, which is our gas constant. Our gas constant is going to depend upon the variables and the units we have. And then we have our Kelvin temperature, right? So that is these are the perfect conditions that don't account for potential energy flux due to the real particle interactions that we might have with gases on planet Earth. So there's one really important takeaway from the kinetic molecular theory. There's probably some more, but the main one is relevant to the fourth postulate specifically. And that is that an increase in the speed of gas particles is going to be associated with the average kinetic energy of that internal system, right? And that's going to have a direct relationship with Kelvin temperature. So if the Kelvin temperature is increasing, then our average kinetic energy in the system will increase as well. So why is this? Well, we have to look at the definition of temperature. So temperature is the average kinetic energy of particles in a system, right? So think about it. Particles are always in motion, they're always shaking, right? They're moving around the internal environment, internal gaseous environment. So if you're going to apply heat to these particles, it's going to make them move faster, which means more collisions, pressure, right? So it's going to inevitably increase the average kinetic energy because of that increase in temperature, and vice versa, right? And then, yeah, so vice versa, meaning that if we decrease the temperature, there's going to be a decrease in the average kinetic energy, decrease in how fast the particles are moving, right? So if we have a cold environment, the particles are going to be slower, right? Okay, well, I hope that makes sense, and I hope that helped. Thank you.